We can see your screen now. Okay.
Yep. Can you see my slides?
Yes.
Okay, great.
Yeah. Thank
Okay,
you.
sure. So,
So
yes,
let me introduce you
yes,
shortly.
please.
So
Yep.
our next speaker is Pei-Hao Shu from. He's a PhD student in University of Cambridge, and he will talk about reward estimation for dialogue policy optimization. So let's welcome Eddie on our school.
Yep. Thank you. Yeah, thanks to Mikhail for inviting me to this talk, and also Julian's introduction to Mikhail. So yes, I'm Eddie Pei-Hao Su. I'm currently a third-year PhD student at University of Cambridge, so supervised by Professor Steve Young. So my research interest centers on reinforcement learning and reward estimation for dialogue policy optimization. Yep. So today in this talk, I will focus on how do we estimate a reward, or for example, how do we evaluate a dialogue to learn a dialogue policy online. So yeah, here we go. So to talk about our focus before, I want to just roughly introduce the different categories of dialogue systems. So we know that a dialogue system can be roughly separated into a chat-based agent and also a text-oriented systems. So for chat-based agents, in this case, we want the system to talk about everything. So potentially open domain or like wider different across several different domains. So in this case that there aren't any specific goals. And so the main focus on this certain research direction is trying to focus on a conversational flow, whether we can keep the conversation between the human and the system going. So here is like example on like some random chat between the user and the bot itself. So from the research point of view, lots of work has been focusing on different variants of the sequence-to-sequence model that was proposed in 2014. So for example, the very first neural conversational model proposed by Google Brain, and also some hierarchical encoder-decoder structure proposed by Montreal and also some other different institutes. They're trying to improve the contextual information and also the response diversity. So this is basically what's going on in the chat-based agent currently. So on the other hand, we also have a task-oriented system, where the system is trying to achieve some certain task. So in this case, because we want to kind of finish some certain task, so we need to kind of focus on some closed domain or smaller domain, because you need to kind of like ground what the user is actually talking about. So traditionally, this is kind of like a combination between some rules and statistical components. And as I said that, because we are actually achieving some certain task, so we usually have some knowledge base where we need to ground what the user is talking about. So for example, we want to have like some information searching system. And then in this case, the system needs to understand whether the user is talking about north or south. So there are also like two mainstreamed on top of this text-oriented system, which is the very traditional pipeline dialogue systems, which is the part that our lab back in Cambridge has been focused on for the past 10 years or more. So on the other hand, they are capitalizing the success of using deep neural network. Lots of people has trying to focus on how can we try to train the entire dialogue system in an end-to-end fashion. Yep. So these are like several different directions within the text-oriented systems, and which are kind of like interesting. And from our point of view, in this certain talk, we will be talking about the text-oriented system in the following slides. Because as you can see that chat-based system is essentially trying to come up with a reasonable response rather than actually fulfill some certain goal or be functional. On the other hand, the text-oriented systems can actually help you to achieve certain tasks, which is more like your personal assistant that can help you deal with some like lots of information gathering and also some like booking or some other like event setting events. So here we want to focus on taxi-guided systems. So you can see that given the conversation between a system, which is the blue bars, and the user, which is in orange, typically when we want to train this kind of systems, we need to get some user, right? So these users are typically kind of recruited from some online platforms. Yep, and we can give them some certain task information to follow. So here, for example, this is in a restaurant seeking domain, Cambridge restaurant seeking domain, where we ask the user to provide some information to the system in order to ask about the phone and address of this certain restaurant. So you can see that throughout this entire conversation, the system actually reply properly to some of the user's query. So, and also you can see that user is asking for a cheap Chinese restaurant in the West, and the system is providing the address information to the system. So according to this certain task information, the prior knowledge, we can try to evaluate whether this is a successful dialogue or not. So successful dialogue means whether all the constraints presented in this task has been fulfilled by the system or not. So as you can see here in this example, objectively, in our case, we have like objective measurement, which is according to this test. It is rated as a failed dialogue because you see that no phone information has been provided from the system side. On the other hand, if we ask the user to rate this dialogue, and so where we call it as a subjective rating, it's actually kind of like successful dialogue because this user has gotten all he asked from the systems. Because you see that maybe he didn't really pay attention to the phone information presented in the task, and like end up didn't ask it, and the system was actually like doing quite well on the user's question itself. So you can see that actually there are some issues in these kind of training imperative. So on the left-hand side, you see that because in this way, we typically need to have a paid user, which need to follow a certain task, which is kind of like non-practical because normally ideally we want to have a system deploy like in a while, and the user you can try to talk with different kinds of user to fulfill their own goal in their own mind, rather than this kind of like explicitly like insert some certain goal on all those users. On the right-hand side, we can see that by using different evaluation metrics, there are actually some mismatch between them. So this will like result in kind of like ambiguous whether this is actually a good or bad dialogue. Yep. So given these problems and issues, here in our task, we wanted to define a proper learning objective, which is a reward in reinforcement learning stuff, to train a dialogue system online from real users. So in the following slides, we want to evaluate dialogue. On the other hand, like that is to say, we want to model a reward for the dialogue systems, and also we want to deal with some unreliable user ratings because it's essentially we want the user to rate our dialogue, but we don't really trust them too much. And finally, we want to use this reward model to learn useful dialogue policy to talk naturally to the real users anywhere. So the models involve, I'll be talking about some recurrent neural network and Gaussian process, which is a Bayesian model. And for the method itself, the focus will be on reinforcement learning, and I'll be talking about some online learning scenarios and active learning. So this is our online. So following the previous slides, our motivation is that we want to learn from real users. So looking back into pipeline spoken dialogue systems, I'm pretty sure that most of you has some rough idea on how dialogue system works. Yeah, but here I'll just introduce it quite fastly. So for the first component of this dialogue system is ASR, the speech recognizer, which transcribes the user speech into the hypothesis of text. So here, for example, we have top end result on what the user is actually talking about. And later on, after we have this transcribed text, we want to determine what the user is actually talking about in the semantic level. So here we have a semantic decoder and a belief tracker, which determine the semantics of the user's speech in a one-turn level or in a multi-turn level. So here, for example, the belief state tracker. So here, in this example, we show that we want to determine the distribution, a probability distribution over all the area we are interested in. So this is the understanding part. So after we determine what the user is talking about, we want to determine what to reply back, right? So the dialogue policy is trying to come up with a reasonable action, a reaction back to the user. Here, for example, it is trying to inform some restaurant which is in the area of West, given what the user is talking about. Here, for example, the system thinks that the user is asking for some restaurant in the West. So finally, after the dialogue policy determined what conceptual representation back to the user, we have some speech generation component, which is natural language generation, and text-to-speech, which is speech synthesizer, to try to realize these high-level representation back to natural language and talk back to the user. So all in all, this is generally a pipeline spoken dialogue systems where we have several components to focus on. So in the following part, I will be focused on the dialogue policy learning part. So from a reinforced learning point of view. So talking about reinforced learning, I just want to give you some some very quick introduction on how it works and how we apply it to dialogue systems. So generally speaking, a reinforcement learning agent is interacting with the environment itself. So the goal of this agent is trying to come up with a sequence of action which can maximize the reward it gets from the environment. So here, as you can see, the agent learns to take actions to maximize the total reward. So, and on the other hand, the environment will also provide some observation to the agents and to kind of understand what's going on in this entire world. So one very famous application of using reinforcement learning is AlphaGo, right? So I'm pretty sure that most of you have heard about this stuff. So it has beaten 2 Go champions, both in this year and last year. So it is actually showing that this kind of reinforcement learning agent, although it's notoriously hard to train, but it is actually working after we can have some useful way to come up with a good agent. So you can see that in this case that the observation of the system is actually the move from its own opponent, and also of course the action itself is its own next move. So the reward it gets will be either win a goal or lose it, or otherwise zero, intermediate, during the entire game. So if we apply this to a dialogue policy itself, we can actually view the environment as the user itself. And also the observation and action will be the thing that I was talking about, the probability over what the user is thinking about, and its own reply back to the user in either natural language or some higher level representation in this case. And of course, the reward itself can be roughly said to be either a successful dialogue or a failed dialogue. So you can see that in this case, a reinforcement learning system is trying to achieve some certain goal. And these goals can be set seamlessly on text-oriented systems, whether the system can actually fulfill the user need, which is kind of like presenting in the text or on their own mind. So, so this is coming back to the entire pipeline systems. The environment is the user itself, as I just said, and the observation is decoded from the speech understanding component, and also the action itself will be later on passed to the speech generation component, and also, of course, the dialog policy itself. So on top of all these settings on using reinforcement learning framework for dialogue systems, one very crucial factor on this stuff is what are we learning for? What are we aiming to achieve? So this comes to the introduction for the reward itself. As you can see that the correct rewards are a crucial factor in learning a good and reasonable dialogue policy. So yes, in the following slide, this is what we want to focus. So a reward for reinforcement learning is actually the evaluation for spoken dialogue systems. And as you can see that dialogue is a very special reinforcement learning task where we have human involving in both the interaction and also the rating, which is the evaluation or the reward itself. So as you can imagine that, like as opposed to like standard reinforcement learning tasks, for example, like Atari games or some robotic task, where we have some clear goal on whether we can win a game or whether we can grab some certain object. So here, the system is not only interacting with the environment, which is some human itself, but also user is like getting involved in determining whether this is a good or bad conversation. So this is a fully human-in-the-loop framework where we know that human is troublesome because lots of people they just don't really follow the task or like play rightfully. Yep. But this is very useful because essentially spoken dialogue systems is created to talk to us, to talk to our human being. So this is a very important factor that we need to deal with every single situations that the human can create. So talking about rating, yes, so rating a dialogue, evaluating a dialogue is it has been a very like a crucial topic like along this and several years. So here, for example, like by simply rating a dialogue, we can rate its correctness, some appropriateness, and adequacy. So we heard about lots of ways to evaluate dialogue. For example, using some machine translation metrics such as Blue Score or Roach or Meteor from language summarization. But as you can see that all these automatic metrics are used to calculate some overlap between our golden standard and what the system produce. But in this case that like there is actually lots of different way to reply back to some certain users. So for example, if I tell a person that you're handsome, but in this case that, I don't know whether you are handsome, but in this case that he can either say, yes, thank you, or he can create some other different sentence in different topics. So it's kind of very hard to, it's kind of very hard and very wrong to use all these automatic metrics to determine whether some certain sentence is the best like response back to the user. So on the other hand, like if we focus on task-oriented systems, because in this case we have some clear goal whether some task is kind of is actually fulfilled or not. So in this case, we have a much clearer goal to focus on rather than all those kind of like vague way to determine whether it is a good response. And so actually you can think about that. To evaluate the dialogue, we can have either a semantic, from a semantic point of view, and also a syntactic point of view. For a semantic point of view, you can think about whether the system is responding with the right topic or semantic level information. And also for syntactic, we can check whether the system is providing a grammatically correct response or not. So here in our case, we will be focused on a semantic part, which is highly aligned to the text success or not. So talking about different ratings, we can have several sources to rate the model, right? So first of all, we can definitely ask for experts, but you can see that it's a very high cost. You need to pay a lot and need to wait for a very long time for them to finish rating. So usually it will result in very high quality systems, but it's kind of like hard to scale up because you need to, for this kind of like iterative process will take you forever. On the other hand, for user rating, it's like less costly because you can ask every single user to rate the model, but it's kind of unreliable because they aren't expert and also they aren't that committed. Last but not least, we can talk about the objective rating. We can have several automatic way to check this dialog, right? So just like the blue score or meteor score or the objective rating that I talked about in the very first slides. So you can see that we don't need any additional human labor on top of that, so it's kind of very low cost, but there is some issue on top of that. So for reinforcement learning signal in spoken dialogue system, typically for this kind of reward function, we usually set a per turn penalty, -1, to shorten the dialogue because the faster the system can provide useful information to the user, the better, right? On the other hand, we also set a large reward at the completion of the dialogue if it is considered as a successful one. So as I mentioned that it typically requires some prior knowledge of the task. For example, the small box on the left-hand side in the very beginning, in the slide in the very beginning. So you can see that this prior knowledge information is actually very useful if you want to train the dialogue system in simulation. So this kind of simulated user will be presented a task given by ourselves. And so in this case, this is actually their goal in mind, and they will try to follow the task in order to talk to the system wholeheartedly. So this is fully applicable. If we want to use this prior knowledge to train the model with some paid users, for example, like a user from Amazon Mechanical Turk or some other online platforms, it is also applicable, but it has some potential issue that I just mentioned in the very first slides, where we have different like evaluation metrics and there is some mismatch between them. And finally, if we want to apply this prior kind of learning paradigm to real users, this is inapplicable because in this case, every single real user has their own goal, and by the end of the dialogue, we will have no reference to check whether the system is actually doing well or not. So this is some motivation of what and how and why we want to learn for dialogue from real users. So how do we learn it from it? So a very straightforward way to learn from real user is that we can kind of infer some success information directly from past dialogues. So in our previous work, we train a recurrent neural network model to estimate whether this certain dialogue is successful or not. So here, for example, given a dialogue of turn big T, for each turn we have some alternative feature covering what the user says and what the system replied in each single turn. So by feeding all of them sequentially into a vanilla RNN or LSTM or GRU, we can have some label determining whether this dialogue is successful or not. So you see that by collecting a set of offline data to train this RNN model, we can come up with a model that can actually predict whether the new incoming dialogue is successful or not. So this output can later on serve as a reinforcement signal to learn a policy. So here are some results on using these the proposed RNN reward estimator to learn the dialogue policy itself. as opposed to the traditional where we need the objective measurement, like the objective measurement, which is rating the dialog according to the text information itself. So on the left-hand side, you can see that the x-axis is the training dialog numbers, and the y-axis is the moving average reward. So you can see that the proposed model is which is the green curve with yellow variance. It's actually learning comparable to the original objective baseline systems. So, but on the other hand, it doesn't need any task information or user feedback, right? So after the interaction between the user and the system, we don't need to ask the user to rate the model, but we simply use this reward RNN model to give us the rating on whether this is successful or not, to later on train the dialog policy. As opposed, the original objective baseline needs the text information to check whether all those constraints has been fulfilled one by one, which is much impractical. So the second benefit of using this RNN estimator is that we can actually learn from every single dialog, because in this case, that after interaction between the user and the systems, we don't need their feedback. We just simply use the prediction from the RNN system to to learn the policy. As opposed, as I mentioned that in the very first slides and in the very first example, there are some mismatch between the objective measurement and the user's rating. So in order to make our training dialogues cleaner, in order to have a better policy, we normally, in this case, it usually use only the dialogues with a match between objective and subjective. So as you can imagine, this will actually result in lots of dialogue that is not actually used for training dialogue, for training the dialogue policy itself. So you see that like this is the previous one. So like although it is so both of the model was trained using 500 dialogue, but actually for the objective baseline, it requires up to around 900 dialogues in total to get comparable performance to the RNN proposed systems. So some summary on this certain slide is that this kind of like reward estimator can help learn the policy in a more practical way and more efficiently than the very original objective baseline. So this is one way to learn an actual dialog policy from real user without their own noisy rating itself. So this is the first way. So on the other hand, what if we focus back to the user rating itself and just directly ask whether the user thinks this is a good dialog or not after the interaction? So, and like intuitively, like this is kind of hard because the user rating are typically unreliable, which is noisy. They are not that committed or dedicated to rate the system itself, right? So in this case, we need to ask them to play with our system, to talk to our system, and also to rate it. But not most of the people, they aren't that engaged in this kind of entire process. After they finish talking to the system, they just simply hang up the phone or like stop the system. And so you see that it's kind of noisy and also difficult and costly to get this kind of label itself. So here, in order to mitigate these problems, we come up with a robust user rating model, which was presented in ACO last year in Berlin. So to handle these two issues, we use a Gaussian process with uncertainty measurement to deal with the noisy user rating. And also, in order to reduce the annotation cost, we use active learning to help determine some useful query rather than asking the user rating all the time. So this is some proposed framework for this for the second part of the work, which is the online GP learning stuff. So just to recap, that we want to learn a real model on top of the user rating for learning the entire dialog policy. So for the rough system framework, this is how it looks like. Given a set of conversation, we want to determine whether it is successful or not. So this reward model typically needs some rating, which is the label from the real user itself, to train its own predictions. And in this way, because the way we mention this as a query is that we want to use active learning to determine when should we query the user rating rather than accident all the time. And on the other hand, because dialogue, every single dialogue have different length in general. So in order to learn this kind of like real model on the fixed length input, we come up with embedding functions that trying to map the very length dialogue into one single fixed length dialogue representation. So the goal is that we want to model a reward on a user's binary success rating. So later on, these rating will be served as a reinforcement learning signal to learn the policy itself. And I will be talking about these two parts in details in the following slides. So for A, the embedding functions. Hi, can you guys hear me?
Yeah, we can hear you.
Okay, yeah. Okay, great. I saw somebody nodding their head. Okay, great. So where did you guys miss my presentation?
On the slide
Yeah,
with the user rating, red arrow down, the A part
right,
of the
I see.
framework.
Okay, sure. So I think that I know where it was missing. So okay, just a moment. I will be sharing my own screen right now. Yeah, can you see my slides?
Yes.
Okay, so this was the part. This was the place where we lost the connection, right?
Yeah.
Okay, cool. So yeah, so here in this case, like in the proposed online learning systems, we want to learn a real model on top of what the user is rating on whether the dialogue is successful or not. So as I mentioned that because here we focus on the binary success rating from the user side. We want to model this user rating model as a reward. So you see that, so given any single dialogue, we want to determine whether it is a successful or a failed dialogue. So for this reward model, it is actually sometimes querying some rating from the real user itself in order to get more useful information to train its own prediction. So on the other hand, because for these kind of dialogue or conversation, every single dialogue has different length of the conversation, right? So in order to learn a real model on a fixed length representation, we come up with an embedded function, which trying to map every single dialogue with varying length to a fixed length dialogue representation itself. And later on, we can learn a real model to determine a successful or failed label, and use this as our reinforcement learning signal to train the dialogue policy. So in the following slide, I'll be talking about these two parts, the embedding function and the reward model in more details. So talking about embedding functions, we want to map the dialogue sequence to a fixed length vector. So here is an example of the dialogue where we can zoom into a turn level interaction between the user and the systems. So for example, turn 1 or turn 2. So here we can actually extract some useful knowledge from what the user is asking for and what the system has replied to this user. So for example, we have a turn level feature vector, which is a concatenation of some distribution over what the user is thinking about, and some one-hot system action representing what the system is replying back to the user in a higher level conception. And also, we can use some additional information such as turn to help us determine where we are at every single situation. And of course, this certain feature vector can extend to using natural language or some n-gram features to capture some syntactic and semantic information or not. So these turn-level features will be later on serve as our training data to train our dialogue embedding. So for dialogue embedding, we have two different ways to obtain it. So first of all, we can use a supervised way to obtain a dialogue embedding, where we simply reuse the supervised recurrent neural network that I just proposed in the previous slides. So here you can basically see that we can actually use the last vector within this hidden layer of the RNN to serve as our dialogue representation. The D supervised DS to serve a fixed length representation on this kind of variable length dialogue. So in this way, it's kind of very straightforward to get this very easily. And on the other hand, we can also have a unsupervised way to trying to come up with a useful dialogue embedding function. So here we use a bidirectional LSTM encoder-decoder, which is a variant of a sequence-to-sequence model. So the goal of this, the training criterion of this certain model is trying to reconstruct the input F1 to FT or to F1 prompt to FT prompt, is trying to reconstruct it as perfect as possible. So from the encoder side, we use bidirectional LSTM to capture both the forward information and the backward information. And later on, we simply cascade all these two hidden layers at every single turn, and then trying to take an average over all these hidden layers in order to come up with a bottleneck feature, which is a bottleneck representation, which is the unsupervised DU, which is, so this is actually simply the average over all these turn level hidden layers from two different forward backward models. So as I mentioned that the training criterion is trying to minimize the output from what the systems produce. So here, for example, given these dialogue representation, condition on this, we want to generate exactly the same input as we input to this certain model itself. So so here we simply want to minimize this MSE training errors. So having this model well trained, we can have both a supervised dialogue representation and a supervised dialogue representation that I just mentioned in the previous slide. And we can actually use these two different ways to map the original dialogue with variable length into a single fixed length vector. So later on, having this kind of fixed length vector, we want to learn the real model on top of that. So here the real model is trying to determine a class probability of either +1 or -1 for successful and failed one, given the current dialogue representation, small d, and some corpora and the corpus of previous dialogue and their corresponding label that we have collected so far. So as I mentioned, that user rating is normally noisy and costly. So here we want to handle both these cases by using a Gaussian process with an active learning scenario. So just to give you some very basic introduction on how and what Gaussian process is. So so Gaussian process is a basic model which is which has been shown to be very useful in pulsar learning in different literature before. So it is defined by the use of some kernel functions where it can help us to learn a reasonable policy from a very few observations itself. So in this case, imagine that you have a very big unexplored space. Because we have a kernel function that can help you to determine some similarity between the space you have been explored so far and some other unexplored space that you haven't visited yet. So in this case, this kernel function can help you to determine what's going on in some certain unobserved space, like when you are trying to explore more on the entire space. So and also as a Bayesian model, it provides a measure of uncertainty on its own prediction itself, which is very helpful for us to determine where we should explore, which unexplored part we should move to. So, and this has been shown to be very useful for reinforcement learning because, as you can, as you know, that when we are trying to do the exploration, a trade-off between exploration and exploitation. Normally, for epsilon greedy method, we are just simply explore the space randomly, right? But on the other hand, this kind of by using this kind of uncertainty measurement, we can have some more information to see which part is much more informative if we explore more, if we move toward this direction. So yeah, so here we use a Gaussian process classifier to determine whether this is binary successful information or not. So as you can see that we want to determine the probability on the success information on the success of the dialogue itself, which is the label y equals to 1, given the dialogue representation d on the x-axis. So here you can see that there is a curve determining what is the probability across different representations. So this predictive model is actually related to a latent function, which trying to map the space of the original dialogue representation to a single scalar, in this case, to a single unbounded scalar. So by using a probit function, we can squeeze these unbounded scalar into a value between 0 and 1 to serve as our probability on whether this is successful or not. So this latent function is usually given, in this case, is given a Gaussian process prior with a mean vector and a covariance matrix. So here you can see that a covariance matrix, we set it as an RBF kernel, which is Gaussian kernel. So a covariance matrix can be viewed as some similarity function determining how close two different dialog representation or two different given input are by using this function. So you can see that there are some hyperparameters, which is P and then scale L, that can help us to trying to fit the the observed sample that we have collected so far. So this is some rough idea on how Gaussian process is used for determining the success information amount. So as you can see that given this Gaussian prior in this place, we have a predictive distribution over the successful dialogues. And whenever we are given a dialog representation T star in this way here, as you can see, D star, we can actually map it to see its corresponding mean value and covariance value, and like covariance in this case, as you can see in this cursor. So by using the probability function, we can see that this is how these two functions are related. We can actually see that whenever this certain term approaches to 0, the resulting probability, which is here, will be very close to 0.5. So 0.5 means that the model is very uncertain on its own prediction on whether it is a success or not, right? As opposed to some values close to 1, where the model thinks that it is highly probable that this is a successful dialog, or some number here, for vice versa. So as you can see that whenever the variance term grows grows up, this certain term will become 0 and resulting in a more uncertain model itself. So as we said that we want to handle noisy and costly. So here for the RBF kernel, for the covariance matrix itself, we add an additional user rating noise in order to capture the noisiness that we have, the noisiness on the user rating that we have collected so far. So as you can see that whenever this term grows, that is like more, whether it is much more noisy, this covariance matrix term will grow on top of that, right? And resulting in this variance term growth, I mean the denominator grows, and like making the final prediction closer to 0.5, where we can make the system much less certain on itself, right? So this noise term in the RBF kernel can help us determine whether the current model prediction is it should trust its own prediction more or not. On the other hand, by having these by having the final prediction on whether the success probability is or not, we can set some predefined threshold on the system's prediction. So here, for example, within the green area, this means that the system, if the system's prediction lies within the green area, that means that its own it is quite uncertain on its own prediction, right? And on the other hand, if the predictive result, if the prediction lies within these two blue regions, that means that it is quite certain on its own prediction. So, so in this case, if the prediction lies within this green area, then the system will query the user to label this certain dialog. On the other hand, if we are in the blue one, we will simply trust its own prediction and use this prediction as a reverse reinforcement signal to train the dialog policy itself. Yeah. So to sum up, these two models trying to map the dialog sequence into, at least the first one is trying to map the dialog sequence into a fixed vector, and the second one is trying to determine whether this dialog is successful or not in a Bayesian way, given the fixed vector that we feed to the system itself. So talking about active learning, as you can see that, so this is a very general, some very classic diagram on different categories of for active learning. So for there are two main active learning scenarios where we have a pool-based system on the bottom here. So in this case, we normally have a set of unlabeled data within some certain pool. So the goal of this active learning agent is trying to determine, trying to pick useful unlabeled data to query the expert. So here, the oracle itself, to in order to get the label on it, to help explore the to help explore these the uncertainty space that the system needs to explore itself. So in this case, that the model is trying to select the best query, the best sample to query from the user. On the other hand, there is another category called a stream-based selective sampling, a stream-based active learning, where we don't have a pool of enabled data, but instead we are the model is given every single sample each time, and it needs to decide whether it wants to query the user or to discard it. And so in our case, our scenario fits much more to the stream-based selective sampling scenario. So stream-based is actually also called online active learning. So this is actually why we will be phrasing our model as an online GP model later in the following slides. And on the other hand, there is a slight difference between this entire active learning scenario is that because we are querying some random user that has been talking to the system. So we might be collecting some noisy rating on top of that. So that's why we I spent some time mentioning how do we deal with these kind of like noisy rating from an average user that we like recruited online from Amazon Mechanical Turk, for example. So just to recap, the system framework work in the following. We have given a set of dialogues, representation, and a corresponding label. We want to, we can extract some tunable feature from the current dialogue and map them using the embedding function to a fixed length vector, D star. So as you can see that D star, and there's the D star plays at this certain part, and we can see that the corresponding success probability on the predictive success probability of the model itself lies within the green area. So we need to query the user. And so here, for example, the user raised the model as a failed dialogue, and this failed dialogue, this negative label would be served as a real model to train our policy itself. On the other hand, if the model lies in blue one, then we will simply use this rather than ask the user to serve as a reinforcement signal. So here are some experiments that I will be talking about. So first of all, we want to evaluate to see how good are the dialogue representation we created using either supervised or unsupervised way, how good they are. So here we simply visualize the dialogue distribution on the distribution of the dialogue representation that we have created. So for supervised dialogue representation, dialogue embedding, we use some set of labeled restaurant dialogue data, some train separate them into train, validation, and test set. And the dimension of this representation is set to be 32. It can be any number, but here we simply set like some, which I actually tried 16, 32, or 64, but it resulted in very slight difference on top of that. Yeah, so instead I just choose some middle point on top of that. So you can simply play with, you can simply set various kind of number on top of this. It won't change actually too much. So here we use a t-SNE plot to see how our supervised dialogue representation distribute. So as you can see that the y-axis is the dialogue length, and the shape of different samples, for example, the triangle one and the circle one represent either a failed or a successful dialogue. So you can simply easily see that there are like two clear clusters on, for example, the successful one and an unsuccessful one in general. And for most of the case, the unsuccessful one are timeout dialogue, in simulation, and also the successful ones are normally short because, as I mentioned, that it's kind of like task-oriented system. The user won't engage too much as long as they get what they want. So, and you can see that by having a training label, by having a label on each training data, these labels can highly affect the final learned distribution, the learned representation for the dialog, for every single dialog itself. So, so this is just to give you some rough idea on how our supervised dialog embedding works. On the other hand, for unsupervised data, I suppose in this case we don't have any label to train our model. Here we are using the RNN encoder decoder that I just mentioned. So here we use like much more unlabeled data to train the model, because as you can see that like this kind of like unlabeled conversational data is much more easier to collect, to be fetched from the internet or somewhere else, or anywhere else, as opposed to some dialog that needs some careful labeling by some expert or some other users itself. And the dimension of like unsupervised dialog representation is said to be 64, which is the size, the double of the size of the supervised embedding, because like we have bidirectional FCM in our input side. So yeah, so this is another heuristic setting. So this is like the distribution of all the unsupervised dialog representation on the t-SNE plot. So as you can see that it doesn't really like there aren't any explicit clusters in the plot, because we don't have a clear label to train these model, right? So by training these embedding functions in a supervised way, it is trying to determine the similarity between each samples, like by their own input feature itself. But like so this is roughly how it looks like. But we can actually see some interesting distribution on top of that, right? So there's a clear color gradient from the top left to bottom right, representing shorter dialogues all the way to longer dialogues. And as you can see, that it's very similar to supervised embedding, right? Successful dialogue are normally less than 10 turns around here, as opposed unsuccessful one are normally much longer, because the user is frustrated. It's like trying very hard to like inform the system, but the system might not understand what the user is talking about and give some random answer. So this conformed to our claim in the very beginning that a user don't engage in a longer dialogue in general in this kind of like task-oriented systems. So we can see that like the length information actually correlates very highly to the successful information, even though we don't have a label, success label itself. So these two plots give us some rough idea on how our dialog embedding works. And later on, we'll be use these two embedding to, we will plug these two embedding to the real model itself to see how it actually helps the dialog policy learning. So this is some like system setup. So like we plug in the embedding function and the real function both into this entire modular-based systems, where we have a red arrow, which is the reward model itself, and we are using a Gaussian process reinforcement learning, another Gaussian process to learn the dialog policy itself. So the domain, the task we are working on is the task Cambridge restaurant domain, which consists of around 100 restaurants, and the users can actually set some constraint to the system. For example, where the area is, some price range, and the food type. And it can actually ask some information from the system on address, phone number, and postcode. So this certain domain has been used in our group for like several years, and it is a rather simple domain, but it can be like help us to see to check whether our proposed model, like preliminary model can work or not. So for the reward setting, as I mentioned, that we have a pretend penalty -1, and by the end of the dialogue, we can have a big reward or not. Depends on whether different evaluation metric thinks that the dialogue is successful or not. So the first one is called the online GP, which is our proposed model. And also, because we mentioned that user rating might be noisy, so here we also use the user subjective rating only to train the model itself. And also, like, we want to compare the second model with the very first model that we proposed, which is called the offline RNN, which was trained from a set of simulated data that I collected beforehand, some offline data. So these are some model that I want to compare with our proposed model. So and the user are all recruited from Amazon Mechanical Turk, where we paid in some money, given their interaction and rating to our system. So this is the learning curve of the dialog policy. So the x-axis is the training dialog number, and the y-axis is the subjective success rating from the user itself. So for the online GP methods, by using two different embedding functions, the supervised one and the supervised one, we can see that there aren't a statistically difference on the performance using two different models itself. They have like roughly similar performance, which can actually help the dialog policy to learn. So, however, as you see that for supervised embedding, it requires some additional label, which is very costly and very hard to annotate on top of all these conversational data we have collected. So, so for the following part, we use a supervised method, an unsupervised dialog embedding to serve as our embedding function in order to compare it to all other different models. So here is some rough the performance of all the proposed model. So first of all, the online GP one, which is the black curve, and the subjective model, which is the orange one, and finally the offline recurrent neural network estimator, which is the blue curve. So you can see that all these models, all these proposed systems achieve more than 85 success rate after 500 dialogues in either you can see from the learning curve and also the final some statistics within some certain regions. So first we want to talk about the offline RNN. We can see that offline RNN actually works quite well on this certain domain, which is the restaurant domain. But there is one critical issue on this certain proposed system, is that because it is training from some offline data, which might distribute quite differently to the online data that we are focusing on. This case, for example, these 500 dialogues might distribute very different to the data that has been used to train this model. Like in this case, the scalability of this model is quite limited because so here the domain that we're focusing on is actually quite small. So the offline data might distribute quite similarly to the online data, but this is not the case when we want to scale up to more complex domain. Yeah, so this is a very big limitation of the proposed the blue curve, which is the offline model. So I suppose for the black and orange one, we are actually asking the user to rate our model, right? So we don't have this kind of issue where there is some mismatch between the training data and the deploying, the interaction that we are viewing online. So the comparison, the reason why we compare these two bars is that we want to see whether our proposed model is much more robust to the noisy user rating. So in order to see the difference, we further train these two models all the way up to around 850 dialogues. And you can see that the proposed online GP model actually helps to learn the dialog policy more robust than the subjective one, the longer one. So as you can see from the left-hand side, the learning curve, and also the right-hand side, the statistics, that there is some statistical difference between these two parts. So as you can see that the proposed uncertainty measurement can help us determine whether the user is actually giving some random rating or not, and further like trust or like don't trust its own predictions. And like by having a much smarter mechanism to deal with these kind of noisy rating, we can have a better result in dialogue policy itself. So on the other hand, one thing worth mentioning is about the number of query for the user feedback itself, right? So as we said that the user rating is normally quite costly. So here, for example, for the subjective system, it is actually querying the user rating all the time, like for every single dialogue, right? So as opposed by having a much active learning mechanism, the online GP model only requires around up to 150 dialogues in order to come up with a robust real model for policy learning itself. So in this case, we can again show the power of the online GP model. So finally, for the conclusion, in this talk, we talk about an online active reward learning framework where we're trying to estimate the rewards for dialogue policy optimization. So we have unsupervised embedding, which is much radical as opposed compared to the supervised one, where we use bidirectional STM encoder decoder. And for an online active reward model, we are using a GP classifier with uncertainty threshold. So in this case, we can reduce the annotation cost from the user label, user rating, and also mitigate the noisy user rating itself. And as you can see that there is no need of any label data for these proposed systems. We're using a supervised one, and and like during online, we directly ask the user rating rather than have collected some like offline label data. And also the entire system is learned online with real human rather than like any user simulation itself. So this can help us to achieve a truly online policy learning from real user without any text information. That as I mentioned, that the final ultimate goal is trying to deploy the system that can talk to any user with their own mind in order to help them to achieve the model, as long as, on the other hand, it can try to update its own policy itself. So, of course, like, so that's all for my current presentation. So, of course, like we can extend our real model into a multi-class scenario, which can try to handle more complex domains, such as a rating of 5 or even much more. And also, talking about the dialogue embedding itself, this is a very similar problem as what we know about word embedding or sentence embedding, right? So because everybody has their own word embedding, and everybody claims that their word embedding is the best, but we know that it's very hard to evaluate. It's very hard to come up with a universal word embedding function that can help you achieve best performance on every single test, right? So most of the time, we can only either visualize them that I just show you, or trying to plug them into some downstream tasks and evaluate them in like different evaluation metrics. I try to show you 2 different ways to see how good my embedding function is, right? So, but there aren't any unified ways to evaluate all of these proposed embedding functions. So this is another interesting direction that people are beginning to focus on. And of course, like these are some off-topic discussion on some general dialogue direction that I think that it's very useful for the following few years. So first of all, how do we transfer the learned policy or the learned model across different domains? How can we transfer these kind of learned knowledge across them? For example, when we learn the model in the restaurant domain, how can we use it to whether it can perform well on all other domains such as hotel or like some more complex like in-car domain? Yep, so this is one very crucial part, whether we can generalize our learning model quite well to some unseen task. On the other hand, talk about the input side. User speech is very ambiguous. So this is as opposed to some image, which we can have some very clear idea on what's going on in the entire image. From what the users is actually talking about is very vague. So for example, when I say that you're quite handsome, right? So do I mean that you look handsome, or do you behavior, or is your behavior handsome, right? So there are lots of different underlying meanings from what every single person is talking about. So to determine this kind of ambiguity to handle it is kind of like an interesting and hard problem that we have been working on so far. And also whether we can learn to reply in a richer context, for example, like if your model can learn to generate much more diverse response, or like in a reasonable way. This is another interesting thing to work on. And finally, here we focus on the task-oriented scenario, where we need to ground the user's input, and in order to come up with some useful reply. And I suppose for pure chatbot-based system, like it can use every single input and output pair of of the combination between two different sources, right? So in this case, it's very crucial to collect high quality data in order to come up with a better task-oriented systems in either whether the system can produce a much more response with much more variety, and also whether and on the other hand, it can actually serve the actual goal that we are actually achieving for. So to get a very high quality data, this is actually a very crucial part in order to further push the dialogue research into the next level. Currently, for task-oriented system, the domain we are focused on is just too small, and we definitely need to reach this into either multi-domain or a much more complex, like the dialogue conversation itself. So so finally, I would like to say thank you to my past and our past and present member in our dialogue group. So Professor Steve Young, who are my supervisor, and Dr. Melissa Gossage, who is my advisor, and also some members in our group, and also some financial support that I have received from either Taiwan and also Cambridge and our department. So thank you. Yep, so these are some reference that I have been talking in the entire slides. And so I'm happy to take any question if you have any.
Okay, any questions, please? Yes.
As you mentioned in the discussions, what could be the issue when you extend your research into the multi-class score? Because the evaluation criteria for this competition is the quality, breadth, and engagement of the dialogue. So it could be the score between 0 to 5. So maybe it is different from the binary task success or fail. Yeah.
Yeah, this is an interesting question. Because I was actually asked from some other source during the conference last year, and also like 2 years before, because essentially we want to focus on a much more complex labeling task, right? So a very straightforward way to extend this model is we can simply extend it to multi-class classification test, right? Because in this case, in our case, the actual output is, so for example, if you're talking about neural network, right? So we are simply replacing the sigmoid function into a softmax, right? Over like much more class labels in this case. Right? So this is for this kind of like task, this is very natural to extend it, and I think that's this is basically some very straightforward way to answer your question, I think.
Any other questions? And so, continuing the previous question, so what your suggestion if we move from goal-directed system to less goal-directed system? What would be your solution for evaluation of such systems? For example, in our competition, we have a system which should discuss some part of the Wikipedia article with the user. So what is the best way to evaluate responses of such dialogue system?
Okay, so I think this is a very interesting question. It's always very hard to evaluate non-text-oriented systems because, as I mentioned, that there are like infinite way to infinite good response to, given a certain question itself. So of course, you can definitely use the automatic metrics such as Blue Score, which is very widely used currently in dialogue research itself, just to give you some rough idea on whether the system can actually learn to overfit to your input, right? So yeah, so in this case, like so just like machine translation, whether the machine translation, so Blue Score for machine translation is actually a very natural evaluation metrics because like given some like, okay, for example, input Chinese, we have some golden standard on whether it should be translated, but not like the like dialogue system where we have various kind of like reply to this certain question. So I think that you definitely can start from these automatic metrics, but eventually I think that the best way is to deploy the system to the real user and ask for their own rating. So for example, you can have two different ways. Like first of all, you can give users some classic label, for example, 1 to 5, to rate this kind of dialogue response. Or further, you can put two different systems. We can present two different systems to this user and ask them to rate the preference on top of them. But I think the second one is actually better because like you know, like three. Like out of 1 to 5, this kind of like score, 3 and 4 is actually very hard to distinguish in between, right? So, and it's very like subjective. But I suppose that when you were presented two different response, you can have some rough idea on given some preference on one over the other one. Yeah. So. So to answer your question, the bottom line is that I think that the human evaluation is necessary if you actually want to come up with a useful either chatbot or task-oriented systems.
Okay, thank you. Other questions, please? No? So thank you for your very interesting and great lecture.
Yep, thanks a lot.
Sorry for the inconvenience with connections and stuff like that.
Yep, sure, no worries. So yeah, so I will be posting my slide on my own website. So if you're interested, you can download over there. And if you have any further questions, just feel free to send me a mail. Yeah, I will be happy to answer any of your questions.
Yeah, we also place link to your slides on our webpage, and we have also translated your talk. So we will give you a link to your recorded video of your talk.
Okay, yep, cool. That's great. Thanks a lot.
Thank you. Bye.
Okay, have a good night.